Hello, everyone. Welcome to the fall 2020 session of the OVS conference. My name is Chatterjee. I work for the Ethernet product group inside Intel. Today, my co-worker Namrata and I are going to talk about an integration of two interesting and powerful technologies, OVS and p4. This is a standard disclaimer from Intel in case of performance claims made in presentation, but we are not going to make any performance claims in this presentation, so we'll skip that one. Today in the agenda, we are going to talk about p4 and OVS and what's the prior work done in integrating the two. When we do hardware offload of OVS, what are the challenges? And what's the approach that we inside Intel are taking? That's what the talk is going to be based on. So if we look at OVS as the cloud computing became more and more ubiquitous, as there was a lot of both north-south and east-west traffic going on between the virtual machines carrying different types of application workloads. A need for an efficient software virtual switch became apparent, and that's how OVS emerged and became very, very successful. OVS has support for standard networking features such as lag, LSCP, tunneling, port bonding, etc., as well as ECL and QoS policies. It is nicely integrated with the SDN controller through Openflow. It has seen widespread adoption. It has become somewhat like a layer 8 on the 7-layer network on top of the 7-layer networking stack. And it has seen pretty widespread support in both the Linux kernel as well as user space. Satisfying a somewhat different requirement, p4 emerged in 2014 as a protocol-independent packet processing language. It allows the network to be described in a top-down manner instead of a ASIC-specific or vendor-centric bottoms-up view. p4 is based on an intrinsic support for a match action pipeline for packet processing and handling of associated metadata. And in subsequent years, p4 also gained in popularity. And now 6 years later, we are still waiting for the next major innovation to happen. But in the meanwhile, we see that p4 faces challenges in coding more complex networking features such as connection tracking, whereas OVS, it needs more programmability in the area where most of the action is, that is the ingress and the egress pipeline. So what we need is an integration of the two, and that's what we call an OVS cooked with p4 spice. There were some prior work done in this regard. There was this project PISIS, started by Mohammad Shabazz and others. It consisted of modified OVS code, a p4 to OVS compiler, as well as many software optimization for performance boost. And two of the recent works are by Sander and Thomas. PISIS seemed to focus more on using p4 to describe what the OVS data plane was doing, whereas our focus is on using a p4 defined data path and running OVS on that p4 defined data path. And this p4 defined data path based on the p4 compiler backend used can be implemented on an ASIC, on FPGA, on some other kind of acceleration. So the Other two approaches are mostly software centric and leverages BPF or user space BPF as the packet processing technology. Um, but what we are trying to do actually aligns quite closely with Thomas's work. Here are some of the challenges associated with OVS hardware offload. We all know that OVS Megaflow Cache was a great software optimization idea and gave many benefits, but because of the potential for the tuple space explosion, it can be slow and also has potential of distributed denial of service attack. Also, the OVS's reactive requirement of having the first packet of every new flow to come to the user space to get the uh, matches and actions configured, it results in a pretty high slow path performance requirement, and also maintaining high flow setup rate is a challenge. The other challenge is what I have tried to describe in this slide, that when the packets are coming from the application, the intent is pretty clear that some wants to do some kind of equal rule matching, some wants to do a L2 lookup, some wants to do a L3 lookup. And eventually, when it is hardware offloaded, there will be specific hardware capabilities such as TCAM or exact match engine or longest prefix match engine, where these will get accelerated. But as these packets go through the OVS slow path, gets put in the Openflow tables and then finally merged into the Megaflow cache, some of that intent is lost. This is a critical part of the information, but that information is lost by the time it reaches the hardware. A better approach, an approach that we are advocating, is to skip the caches and offload directly to the hardware tables. And this can solve some of the other associated problems, such as maintaining high flow setup rate. As a hardware vendor, we inside Intel need to support many different platforms. These could be switches, NICs, FPGAs, or even pure optimized software. As a hardware vendor, we also need to support many different types of vSwitches. For instance, custom vSwitches that a certain company may have developed, but don't want to upstream it, as well as OVS lookalikes such as VMware NSXT and VPP and others. Our response to that is to create a p4-driven vSwitch platform that is common, extensible, programmable, and any specific vSwitch such as OVS can be easily supported by simply adding a shim layer on top. And now Namrata is going to present the technology details.
Thank you, Deb. Hi, everyone. I am Namrata Limaye, and I work for the EPG software group as same as Deb at Intel. Deb just went over the current challenges in OVS for hardware offloading, and we believe that there is a need to define better ways to program the hardware and software data planes. P4 has the ability to represent the data path pipeline effectively, and by integrating P4 with OVS, we can bring the pipeline knowledge into the OVS to intelligently design the Openflow or P4 pipelines. I will go over what we are doing at Intel and how we are approaching the P4 integration with OVS. So here is where the spicing up starts. At Intel, we are trying to develop a layer parallel to ofproto, which you see in the picture, and name it as p4proto. The main purpose of which is to directly translate the Openflow table into P4 and offload directly from there. The main functions of p4proto are to build the P4 pipeline from the P4 file, So it contains P4 objects such as tables, actions, counters, meters that are needed for the pipeline. And since this is at the same layer as OFproto, we are going to provide a mapping between the OVS pipeline objects and the P4 objects. The mapping can be provided to the OFproto using enhancements in the OVS kettle current CLIs. So integration of P4 with OVS will also enable explicit encoding of rules for mainly for the underlay and inline functions that are in OVS, such as tunnels, CT, mirror, sample, etc. And I will go over that in the later slide. The p4proto layer will have the capabilities to program multiple data paths, p4 data paths, such as the p4dptk in the software and p4ubpf that Thomas is working on, and also could program the p4 based NICs. To do this, we will have to skip the OVS megaflow and microflow as Deb mentioned, caches, and we will not be used for and they will not be used for programming the data path since we are programming directly from the P4 from the Openflow tables. There will be two different paths now for exception handling. So one could the exception packets could go to OFproto and which could be sent to the OF controller, or it could be handled by p4proto and sent to the p4 controllers. So this also enables proactive programming. So when Openflow tables or P4 tables are populated, because the pipeline is the same as the NIC, it could be just pushed down. The same rule could be pushed down to the NIC with the same key fields and actions. And just like OFproto has the interface to OF controller using Openflow protocol, p4proto will have an interface to p4 controller within OVS using gRPC. So next is how do we implement the OFproto layer. So P4 runtime is an open source, and it is a standard way to control P4 forwarding element, for example, to add and delete entries to the switches forwarding tables. P4 runtime is also silicon independent or pipeline independent, meaning when features are added to the P4 forwarding plane, the API does not change, and there is no need for recompilation or even reboot. So there is a reference application already open sourced, which is called the P4 Runtime API, and we are going to start with using that as to build the OFproto base layer. This provides the gRPC server capability, and so gRPC server capability is usually available on the switches, and the gRPC client usually is the controller. One example of controller is a Sonic that is currently used. There is also another barefoot runtime that is being worked on, and it is going to be open source soon. So Barefoot has developed this to control the Tofino P4 based switches. It is based on P4 runtime, but it offers much richer features and capabilities. And these are some features that P4 runtime supports. So this is how OVS plus P4 runtime looks. So OFproto and p4proto are running in parallel. You can see the match action pipeline. We have derived this match action pipeline from the VMware Andreas pipeline. So it's a realistic example. The pipeline has several tables, as you can see, and even the mirror table for configuration. p4proto is going to be based on P4 runtime, as I said. So it will have 3 layers. It is divided into 3 layers. The topmost layer, the P4 API, is an interface. It provides an API for the OFproto to call. So when we map these tables to the P4proto tables, this API is available to be called to add entries to these tables in the p4proto. And it also provides functions to fetch stats or batching and counters and meters and all of that. So we can provide enhancements to modify the OVS OF kettle current command to provide the mapping within the p4proto, and separate OVS p4 kettle new command can be added to actually add the flows directly into the p4. So the second layer here is p4info. P4info is a data model that is built based on the p4 file. The p4 file is converted to the JSON file using p4c. And this JSON file is actually fed into the p4 runtime, or now p4proto, to build the internal p4 info structures. The third layer is the target data planes. So any of these data planes can be linked to the front end of the p4 runtime. And these work as the current OVS DPIF to talk to the target backend, which is for some cases for RT flow, and for p4nic internal libraries, it could be p4nic pipeline. So as you see, the three pipelines are all the same, and all are and the two of them are driven by the p4 file. So what we did was we worked on worked on the Andrea example to convert the Openflow Andrea pipeline to the p4 file, and we will be building our big p4 NIC pipeline based on that, as well as the p4 runtime based on that. So how do we actually map OVS objects to p4 objects? So OVS bridge basically consists of ofproto and the pipeline, and which is similar to p4 device. It consists of the target pipeline as well. So these can be mapped. These get translated directly. Then we have OVS tables, which could be mapped one-on-one or many-on-one, as we are seeing in Andrea, into the p4 control tables. So for the match field types, OVS supports exact match, bit mask, or wildcard, and p4 supports exact match, ternary, wildcard, or bit mask, or LPM. So we need to define some way to OVS to the p4 tables, and we are thinking that we can provide the static mapping using the OVS command line. So this map table basically maps the entire OVS table to the entire p4 table. The field names can be the same to make it easy. And because OVS is so dynamic in nature, and the flows actually define what goes into the table, we could we could modify the add flow command to introduce the map table and introduce the p4 table name as well as the actions. So OVS priority is an important concept in OVS, and to map this to p4, we will have to define a set priority action in the p4, or map it to some metadata. Mapping of OVS to p4 actions. So OVS has a default action normal, and p4 can keep using that. p4proto can keep using that to use the OVS's L2 switch functionality. These actions could be either defined in the p4 control block, because there are many actions included in the flow, or it could be used via the static mapping as shown above. Now, OVS also has recirculation and resubmit actions, which according to PSA architecture can be written as p4 metadata. Tunnel actions could be defined as p4 macros, and metadata could be directly mapped to metadata. Map action function is going to be provided to map the OVS all basic actions to the p4 actions. So now talking about configurations, mirroring and sampling, lag, and ECMP. These in OVS get applied per flow before the flow is offloaded. But some hardwares can actually support this configuration and do that themselves. So we could actually port this mapping into the p4 config tables and send it down to the hardware. We also have counters, meters, and registers, which can be applied directly to the p4 direct or indirect counters and meters. Direct is per flow, and indirect is the global. I will just show this example to show the mapping that we are doing for the Andrea pipeline. So there is a table in Antria pipeline, which is called the L3 forwarding table, which has tunnels. If you see on the left side, ingress is the tunnel traffic that is coming in from the peer node. It has two match fields, MAC dest and IP dest. So these could be translated. If you see on the right, there is an L3 forwarding ingress table translated directly to the dest address and the dest MAC. The first two entries, and then because this is coming in from the tunnel, it will go through the VXLAN port in the OVS and use the kernel module um, uh, to find out the outer headers and match on that. So that is very implicit in OVS, but here we can explicitly encode these as VXLAN outer header and match on that and program the pipeline based on that. So this is where the explicit encoding comes in. The actions could be defined in a macro, so the actions are combined here above the table definition. Now for the ingress, we have the tunnel traffic destined to the local gateway, or we can destine there's traffic destined to the remote pod via tunnel. So in one case, it is going to the local gateway, so it doesn't need the NCAP. And then the other case is where we need the NCAP. So we have the two actions defined, where one has the NCAP and the other does not have. And this can be, again, explicitly encoded instead of implicitly deriving like OVS. Next example is mirror. This is a configuration example. So the left side is basically what OVS-DB contains for the mirror configuration. And there is the ports from and to, and if the mirror is ingress or not. And these could be defined ternary to give to allow for variations and select all option. And for actions could be mirror to the port or mirror to the VLAN and count. So there is also an annotation, this type config mirror, which tells the hardware that this is actually a configuration and this is not the table in the pipeline. This is an interesting example, and I will focus on the priority and how it can be programmed in the hardware. So this is conjunctions, which has 3 dimensions: network source, network dest, and TP dest. And these 3 actually could be programmed as 3 different tables, which could be processed parallelly in the hardware. All these 3 could set a metadata to say that if the flow matched these tables or not. There is also a priority consideration in the left side of the flows, where the CT established flow has a higher priority than the other flows. So here we have the set priority action, and this CT state could be either in the same subtable or on a different same parallel subtable or on a different table. And the result from all of these can go into a serial next table, which checks the priority and also works on the metadata to execute the actions. For the summary, what did we go over? We created a p4proto parallel to ofproto, and we defined the entire pipeline in p4. We mapped the Openflow pipeline to p4 pipeline for flow rules and configurations using OVS command line. And then we programmed the data plane and skipped megaflow and microflow caches, and also the revalidator stats update to both ofproto and p4proto. So we have some open issues that we would like to collaborate on. And if anybody is interested in the development work, we will be posting this on the GitHub, and we will run the development from there. So if you are interested in collaborating, please contact us. The information is coming up on the next slide. So for the open issues, we need suggestions on whether we should support multiple data planes at the same time. So should we enable one pipeline in p4dpdk and another pipeline in p4nic, and is that even a use case? The second is whether we should run ofproto and p4proto together and upstream the p4proto in the OVS baseline, or we should have different repos and or a different implementation for p4proto and not do the mapping at all. Third is propagating changes. How will we propagate the changes in OVS pipeline to p4 file, and how do we do the ofproto to p4 proto mapping? So this is it. This is our contact information. And as I said, the code will be uploaded on the GitHub very soon. Please contact any of us for collaboration and development work, and we'll be happy to hear from you. Okay, thank you.